I would like to briefly show you why engineers in practice very often use the Laplace transformation to perform vibration analysis. Imagine a vehicle suspension that is excited into oscillation by a road irregularity with an external force F external. As a rough approximation, the system can be simplified and described as a vertical, single degree of freedom oscillator with the coordinate z. The equation of motion is as follows. If we now apply the Laplace transform to this equation, the following happens. From a differential equation, which is generally difficult to handle and solve, we obtain an algebraic equation. More precisely, we obtain here a second-order polynomial with a variable s from the frequency domain. This algebraic equation is very easy to solve. Let me show you. If we factor out z of s from the equation and rearrange it, we obtain a relationship between the output quantity z and the input quantity f in the so-called frequency domain. This ratio is called the transfer function. It generally describes how an input signal is transmitted to the output quantity and represents the complete description of a linear dynamic system. This transfer function is usually denoted as g of s, where the complex variable s is equal to j omega. In most engineering applications, transfer function is used to determine the response of a system to a harmonic excitation, and this is done as follows. We take the transfer function and substitute s with j omega. This complex expression can now be separated into a real part and an imaginary part by multiplying with the complex conjugates. With this real and imaginary part, we now have everything we need to describe the system response. On the one hand, we are interested in the amplitude amplification, meaning how much amplitude the output quantity z produces per input force F. This is calculated as the square roots of the square of the real part plus the square of the imaginary part. In addition, we also need the phase shift, meaning how much the response lags behind the input signal. This is given by the arctangent of the ratio of the imaginary part to the real part and is usually denoted as phi. Both the amplitude amplification, also referred to as the magnitude, and the phase are functions of the excitation frequency omega, or more precisely the frequency ratio of omega to the natural angular frequency of the system omega 0, which is usually denoted as eta. The system response, in this case the vertical oscillation of the oscillator, is given by z of t is equal to z hat times the sine of omega t plus phi. By using the Laplace transformation, we now obtain a highly compact representation of all possible system responses for all possible excitation frequencies without having to apply complicated methods for solving differential equations. For every possible excitation frequency, we can directly observe the magnitudes, which, when multiplied by the input quantity, yields the output amplitudes, as well as the phase shift phi. If you want to learn how to apply all these methods on interesting, real-world engineering applications, and learn how to solve machine dynamic problems like an engineer, check out the first link in the description.